Welcome to the Zoomtown experiment. It's actually been quite a while since I filmed the last story, and that would have been all dealing with the build of the robot. Right now we're going to be transitioning from this point forward into the software or the program that will actually run the Zumi. We're going to talk about that in this episode and cover some of the building blocks or the framework of how I envision this program should operate and so on. We'll also take a quick review of where we're at with the hardware so that you're up to date as well, because this changed all the while developing the code. Now, the thing to keep in mind, I filmed these stories ahead of schedule. So what you're seeing, say, in early March of 24, I'm already probably working on the stories for, say, July or August. So I get to see into the future where you don't. So I want you to kind of rationalize and understand some of the things I'm going to talk about are from way down the road from your perspective. From my perspective, they're already in the past. Now let's take a look at the Zumi itself. The first thing I wanted to point out, this is the latest body design. I just threw a couple googly eyes on there because those always make things more silly and fun. But we've got an opening here for the line of sight sensor, an opening here which will be for our indicator LED, which will either be red or green. The skirt at the bottom of the body comes down just about to the bottom of our line sensor bracket. I stylized it a little bit, tried to give it the Art Deco teardrop style fender flares, but I had to nib the backside a little bit to allow for more clearance as it makes turns. Toward the backside, this gives me access to the switch. Flip that guy over so you get an idea. The switch, which would be here, the flashing LED would be up in this area, and then the push button, and then the power LED is right here. To change batteries, which go into this compartment, the body would have to come off, and that was always the intent. And then the body itself is very thin wall. It's just a shell. I think in 3D printing, there are 4 wall lines to create it. It's quite sturdy for what it is, and it's extremely lightweight. But this will just ultimately slide over the top of the Zumi and rest on 3 standoffs here, here, and here, and then bump up against another standoff in that area. Now, as you can kind of see, this may look different than the last time you've seen it from the build. I discovered an error, actually 2 errors on this circuit board, so I had to put an auxiliary on here to bypass that while I worked out the bugs on that. The line following bracket has changed dramatically several times since the last time you've seen it, and that was to get a little more sturdiness for where the encoders mount, and now they're fully wrapped by this bracket and they're taped in place, and that works really well. The time of flight sensor has changed, so I had to deal with that in the bracket design. The line following sensors down below, they used to be almost flush with the basin. I've moved them up higher into the bracket so that they get a little better broadcast of light and better pickup for the line following. So those changed. Also, the 2 Hall effect sensors, that changed ever so slightly, nothing that you would be concerned with from your perspective. So most of the changes from the original design that you saw earlier on was all in this bracket. The other thing that I ran into that was very problematic, I got a little ahead of myself. Down inside here on the power control deck, which is where we have the dual power supply, I ordered up some what I thought would be very simple PCBs and got them, and then I, of course, realized I hurried through the design And turns out that they don't work. So I got about 20 of these that'll end up in the garbage can, and I have to redo it. At least that was a reminder to do things more cautiously before I finalize the design of this circuit board, so that I don't have 20 more of those going in the garbage can. But I'm working through the design a little bit more yet, even though we're already heavily into the code. Another thing that will change from my original idea, and it was a cost savings decision when I made it, I do want to use DuPont connectors for all of the white jumper wires everywhere I can. So I bought a bunch of these off of AliExpress. They're about a penny a piece, and they're stiff as a board. And they're horrible. They are really, really bad for this application. For a jumper wire on a breadboard, I'd have no trouble using them. But what I've found is that where the crimp and the wire meet together is a very brittle connection, and in all likelihood, you'll do nothing but fight broken connections. I ran into it over and over and over again on many of these connectors while working with it and testing. And it was every time you pick it up or move it, you're touching the wires and moving them ever so slightly. But it's not like I was abusing them. So I got fed up with that, and I reached out to Amazon to find an alternative. And it turns out on Amazon, I got these from Adafruit, or via Amazon, I got them from Adafruit. These are silicone jacketed wires, high flexibility, and they don't come in the ribbon like the other one, but they do come in several colors. I'm just showing you the blue ones here. But these have proved to be much more useful and durable for this application. The downside is one wire off of this is a penny. That's 10 cents. So my cost went up 10 times. But I certainly don't mind investing in the quality if it's going to save my sanity. So that's where I ended up with. So now I got a bunch of nice silicone wire jumpers, and that will hopefully resolve a lot of my electrical problems that I battled over the last few months. So the hardware is still kind of in that developmental stage, and I'm good with that. Hopefully in the next month or so I'll have that all nailed down, and then I can start assembly of all 16 or 18 of these Zumis that I plan to put together. Now at this point, before I get into explaining my conceptual ideas for the program, I have to extend an appreciation. So many of you have been very generous, and I'm amazed by it. You do these super thanks and you donate a small amount of money. I really appreciate that. I really do all of this, obviously, for fun and enjoyment, and I love sharing and doing these sorts of things and helping others. But some of these projects do get really expensive, and this one is getting very expensive. So those donations are absolutely appreciated. They help defray the costs and allowing me to continue with this sort of thing. So thank you so much. Domo arigato gozaimasu. Muchos gracias. Dankeschön. I don't know all the rest. Jinkui. I'm very excited that people appreciate what we're doing here. So again, thank you very much. With that, let's go on to how I conceptualize what we're doing, but we'll start that with a review of kind of where we're at and the components and so forth. Our overall objective with the Zumi control system is to use these devices, 1 PICO W, 2 18650 cells, 3 DC to DC converters, 2 DC gear motors, 2 wheels, 1 ball caster, 1 motor drive, 2 magnetic encoders, 2 Hall effect sensors, 2 photoreflective sensor, 1 time of flight sensor, and a partridge in a pear tree. Oh, I'm sorry, I got off track there. And several 3D printed chassis parts and numerous wires and a whole lot of thinking to get us to this point. Now, this will be used to build a robot that can autonomously navigate through a course using provided directions, sensors for feedback, and arrive at a destination and not get lost, or crash into something, or drive across someone's lawn. Seems very simple, right? To accomplish all of that, we're going to now take a look at what we use for inputs, what is being output, and then what our goal is. So using the inputs of MQTT, it's a communications protocol. We will be using that to communicate to the device I'm calling the scheduler. And that will be the device or the computer running on a Raspberry Pi that will give us driving directions and provide random destinations at random times for the Zumi to get from point A to some point B. So the MQTT communications will provide us with directions, step-by-step driving directions like we would get from our navigation system in our full-size cars. And then object proximity information. And that one is really on the fringes of whether or not I can do it. But I'm going to go down two potential paths with that as this project develops. We're also going to use two magnetic encoders, which will provide odometry or positional data relative to how far it's moved during the current segment of the trip. A trip might consist of 3 or 4 different roads in 3 or 4 different turns. Well, the odometry, we need to keep track of where we are and how far we've traveled on each one of those segments. It will also provide velocity feedback. As the Zumi's moving along, I'll be checking to see how fast I'm going, and I need to report that. That will help with the software in the scheduler to actually predict where I will be in a given point in time in the future. As long as we know velocity and heading, we can figure out a destination or a point forward in time where the Zumi will be. There will be Hall effect sensors that will be reading and looking for traffic control devices. There will be photoreflective sensors that will be giving positional data on the roadway of where the Zumi is. And that'll be along our straight line roads. Those photoreflective sensors sense the position of that line, a marking on the roadway, and that will steer the car so it stays as straight in line as possible. And finally, the other input will be a time of flight sensor, forward-looking to see if there's anything in our path, and then the Zumi will have to deal with that by stopping or slowing down, etc. Now, all of those inputs are to control this singular output, a motor control. The motor control really just drives or controls the motors, but we're telling it very precisely how we want those motors to move in order to navigate and get from point A to point B. It's that simple, per se, right? We need to get from point A to point B, and that's all done by 2 little DC motors attached to 2 3D printed wheels with O-rings for tires. And we've got to do that very accurately. And so that is what we're controlling. All of those inputs and all this logic to control those 2 tiny little motors. And that is to get us to travel to the desired destination. It's that simple. Moving further into this, now let's start taking these concepts and breaking it out into how the program structure should be. There's many different approaches to writing a MicroPython program. Many different styles of programming as well. You could go fully object-oriented or function-oriented, almost inline code with no functions. There's pros and cons to every one of them. And in truth, I really like object-oriented programming with classes, etc. I really like it, but often I'm too lazy to do it, and that's the plain and simple truth of it. It isn't that much more work, but it just adds more to what I already consider a very heavy workload trying to keep up with my pace here. So we'll be using functions. That's the initial design, but that may or may not work as we get into it. The program, every MicroPython program, and frankly almost every Arduino program, you have a main loop, and it just constantly runs, and then it takes care of tasks each iteration through that loop. And often we really don't care how long that loop is, simply because it doesn't matter. But we're in the world of motion control. It's very important to keep track of how long ago it was before we looked at a sensor. Perfect example, I'm figuring out velocity. Well, in a given period of time, I can read the encoder at one point in time and another point in time. Based on a specific time frame, I can then calculate velocity. It will also help me with predictability of where the Zumi will be at any given point in time. So it's very important to me for simplicity and to deal with other aspects of motion control to have a deterministic loop. Deterministic means that it runs every so many milliseconds. In my case, I've targeted 5 milliseconds. I really wanted to target 2 milliseconds, but once I got into some of the very fundamental aspects of the program, reading the sensors, if you remember back when we were doing a lot of testing, we tested how long each sensor took to access it and read the data and get that data perhaps into a more usable value. And it just became very unrealistic to do a 2 millisecond deterministic loop. So I settled on 5 milliseconds. And as time goes on, we're going to get to a point down the road where this is going to get really dicey and very problematic. And that'll probably be about 5 or 6 videos from now. And that'll probably be a side video where I discuss the problems that were encountered at that phase. So we're going to have our main loop running at essentially right now we're saying 200 hertz, which would be 5 milliseconds. Every 5 milliseconds that loop will execute. And during that, we're going to need to perform all of these functions. In communications, we need to perform and process all communications with the scheduler. We need to monitor velocity, so we need to perform velocity control, and the purpose of that is to precisely maintain motor speed while utilizing feedback from sensors and other controls to achieve accurate heading while moving. In association with velocity control, position handling and understanding our position within the environment is very critical. Velocity control and position handling have to go very closely hand in hand. And with the position handler, we need to precisely track the distance traveled using information from sensors, primarily our encoders, to maintain accurate odometry, accurate positional information. While we're moving along, we need to be running a collision avoidance system of some sort, or we're going to be bumping into other Zumis or other objects. And that'll be primarily driven by our time-of-flight sensor that's forward-looking, and its function is to detect objects in the path and take corrective action to avoid a collision. The status indicator is feedback to us humans as the Zumi's moving along. It won't have an LED screen or an LCD screen. It's just going to use a couple of bicolor LEDs to communicate status information. Perhaps red, something's wrong, it's stuck in an error. Green, it's running good. Haven't really figured out what I need to communicate yet with that. And then finally, a trip handler. And that function, its purpose is to read the driving instructions that were sent to it via MQTT from the scheduler, process each segment of instruction, in essence, drive this direction this far, It'll process those driving instructions that are provided by the scheduler to navigate from one location to the other and then move on to the next segment until the end of the trip is reached. So that is you're looking at how I'm going to organize each of the functions of this overall complete program. Now let's take a look at a little more detail as I broke it down further into our main code and the related things that need to be taken care of within the startup, and then from our main loop, looking over to each of the functions. In the startup code, which is usually the header of my programs and right below the commentary, we're going to load our libraries, configure and start the networking and MQTT. Remember, this is Wi-Fi, so we are using networking and we are using MQTT as our communication protocol. We need to configure our PICO hardware, all the I/O pins. We'll need to configure I2C interfaces for the devices that use that. And right now, the only devices using that are the two encoders. We need to define some global data. Yes, I know everybody hates global variables in the world of Python, and frankly, I'm perfectly fine with them. In small applications like this, it's not that difficult to manage. And I've been working with global variables since the early 80s, perhaps even the late 70s. So for me, it's not a big deal, and I don't get all wound up about them. I will also be enabling a watchdog timer to make sure that the Zumi is in fact running and processing data. Should it detect anything wrong, well, then it's going to go through and go into a reset routine, and it'll take care of itself. So all that gets done before we enter the main loop. Inside the main loop, which is running at 5 milliseconds, we need to calculate position, calculate distance to go, perform velocity control, perform communications, and test for the end of the move, and of course a lot of other little details in there. And all that's handled by the functions over here. In our functions for communication, we're going to broadcast our current position and velocity back to the scheduler. That'll be done via MQTT. We will also be getting signals regarding starting the motion or starting the overall simulation, and an override from a velocity override control over at the scheduler, and e-stop inputs. There's an e-stop control on that operator panel. If I hit that button, all the Zumis should come to an immediate stop. And we also will be needing to read and store trip plan information into a list. And that list would store each instruction one by one. So that is communications, and that gets pretty well handled almost every time through the loop. Obviously, when the Zumi is parked, it has more time to deal with some of the more time-consuming operations, such as reading and storing the trip plan into the list. In the velocity control function, we'll go ahead and set the wheel direction, forward or reverse. We'll calculate the distance to decelerate to a lower velocity. That's very important. You'll understand why during that video. We'll be handling the CAS, feedback, overrides from the scheduler, as well as the e-stop signal from the scheduler. We're going to perform acceleration and deceleration within velocity control. We'll perform the line follow steering. Yep, that actually gets done in velocity control. And we're going to perform encoder feedback steering. That is also done in velocity control, or at least I think it will be. Right now it looks like it will. We need to then, when we make a change in velocity, we need to convert that data into a PWM signal. So we'll calculate the PWM duty cycle. We're going to test that for excessive values because the motor controller and the PWM don't like to deal with values outside of its range. And then finally, we'll set the PWM duty cycle for the motor controller. In parallel to that, or I should say right after that, will be the position handler, which will set encoder zeros and offsets. At the start of every motion, the encoder's got to be zeroed out and their offsets preset. And these encoders are absolute, and that's the reason why we need an offset. We will read the encoders, and we will account for any special conditions. You'll learn all about that when we get into the position handler. And then we're going to calculate our current position, which then, as you may recall up here in communications, that will get sent back over to the scheduler. The collision avoidance system, its sole function is to calculate the distance to an object. So it'll perform its read, and then we'll convert that into a useful number. We need to provide status information about what's going on, and that'll be setting the LEDs to the correct colors using on and off signals. The trip handler just simply steps through the driving instructions which are stored in a Python list. And then for each instruction, we'll set the parameters for that motion, and the loop will just execute it as they go by. Finally, we need to monitor our Hall effect sensors, which are essentially at this point only performing the function of looking for stop signs. So if we see that, we'll have to deal with stopping and then recovering from that. Now that's a rough overview of everything that's going on and a very simplified overview. Now it is pretty accurate to what I think the end program will end up being, because this was actually updated throughout the course of development. So some of the operations, especially in velocity control and in position handler, some of the tasks I'm performing in there actually have moved back and forth between those two functions numerous times already. Just how you interpret the data and where it's best utilized to perform some operation. So it's kind of interesting to follow along on this if you're at all interested in motion control, whether it be a robot moving around or a CNC machine or a plotter or a 3D printer. A lot of all of this applies directly to that. Now, as I was going through a lot of this development of the code, and your mind is always looking at everything, even though you're focused on a small task or part of the program. And there are things that have come up that I don't know how I'm going to deal with yet. And the first one is how to deal with two zoomies driving around a corner at the same time and not trigger the collision avoidance system on the zoomie that is on the inside lane. And I'll set up a few objects here on the track, and you can see how as this zoomie's going around the corner, its forward-looking sensor can easily see the car in the oncoming lane. That's a bad thing. Obviously, we don't want this zoomie to stop because that one's driving perfectly safe. So it may be just as simple as disabling it for when we're making a turn, and then turning it back on when we get back onto the straight section of road. But nonetheless, it's going to create problems. Another one is how to avoid a crash when backing out of a driveway and into traffic. That's going to be a really dangerous situation because I've got all these zoomies that could be going in either direction on the roadway, and I'm backing up completely blind. I have no backward sensing. So I'm going to need to rely on the scheduler to help communicate the position of the other zoomies. And that's what I was alluding to earlier in the first slide of this presentation. That's going to get very fun and very tricky. And finally, we've got to come up with a way on how to avoid crashing into a zoomie when making a left turn. Now remember, this is based in the United States, where when we make a left turn, we cross the oncoming traffic. In the UK and Japan and a few other countries, it's the opposite. But conceptually, I will have to stay looking at it from my perspective just because I got to deal with it in logic. But nonetheless, if we're crossing traffic, we got to make sure we're not going to hit the car in front of us. And then there's the rest of the crazy questions that I've had since the beginning of this project and probably why I wanted to do it. Will Zoomtown be nothing more than a demolition derby? We don't know yet. These things could just all not do what we want, run around bumping each other, knock each other off of Zoomtown, the platform. Will the Zoomtown experiment be a total failure? In all likelihood, right now, I think I've got a little bit better than a 50-50 chance, but we really won't know for a good number of months yet. And finally, should Zoomtown have been called Crashtown? Well, that's to be determined yet. So maybe it's a little premature for that question. Hopefully we won't have to answer it with yes. Now, over the course of the coming weeks, I can kind of show you what the schedule is going to look like and how we're going to break this out into the video segments. Covering this entire program, and I'll show you what it looks like right now in tiny text. This is actually the whole program as it exists at the minute, not counting the libraries that are also called in. So all of that is going to be next to impossible to explain in one lengthy video, and it would be incredibly confusing for me as well, trying to explain that. So I'm going to break that out, kind of like how we did the build process. Take it function by function or device by device. So the next video we're going to talk about the main loop, how I'm going to do the framework for the program. That'll get a number of things in place, so as we add other features, all we got to do is add those and not repeat all the steps that were already covered. We'll just wedge this new function into the existing framework. So our first video will be on the main loop. That will then require a few videos to get communications all configured and set up, because we'll need MQTT implemented, installed, and tested on both this, on the PICO and on the scheduler, and then writing the routines of handling that data. Then the next video after that would be our velocity control. That potentially could be 2 videos. There's an awful lot going on in there. The position handler will be a video. Collision avoidance will be a video. Status indicator may wedge in with another one somewhere. And then finally, trip handler. Now at that point, we're going to have a pretty highly functional autonomous robot. It just really won't be refined enough yet to just hit the go button and watch it get around. We're going to have to really work toward developing each of the maneuvers that Zumi has to make. You know, you'd think turns are simple. You're going to find out it's not quite all that simple. And even driving in a straight line, it's not that simple. So we've got to get through all that and get each one of those driving tasks really refined before we can get into multi-car simulations. During the initial testing and build-up of this whole project, I was testing all the sensors, and many of you requested code for those sensors, the code that I was using to test with. I didn't post those very specifically because they weren't really written in a way I was actually going to use them. They were, for the lack of a better word, a fast little hack to get data out of the sensor and look at that data, and primarily also to measure the time it took to do that. There was no intent, no desire or anything to make that code be properly functional or even close to being written in correct Python, if you will. Now that's all going to change in our coming videos, because I will post up on a web page on our companion website the code for each episode. So the program will start out, the very first one I'll post will be our original framework. The next week will be the additional code put into it, and so on and so forth. And of course we get all the way to the end, and then there's probably going to be more changes and then follow on revisions, etc. So I really hope you look forward to following along on this. I think this is the part where it gets a lot more exciting for a lot of you viewers, because you really do seem to lean toward understanding the Python code and how we're trying to do things within that code based on feedback from sensors. Every program is about taking input, processing information, and doing something with that result. In this case, it's kind of a little more fun because things are moving around pretty cool. Well, I think I'll wrap up this video here at this time. And again, I want to express my sincerest appreciation for following along on this, and for those super thanks donations and show of appreciations. I really, really do appreciate that. Thank you very much, and I look forward to seeing you next week.